And today we're going to talk about simplifying expressions with rational exponents. The last time we met, we were talking about the nth roots. We were talking about how to convert a power to a root and back and forth. If you look at this screen right here and you look at 27th to the 2/3, we talked about the fact that the bottom number, the denominator, would become the index. The numerator would become the exponent, and of course the base would become what's called the radicand, or the number underneath the radical symbol. We also talked about that you have sort of a choice. You can either take that squared exponent first and then the cubed root, or the other way around. And we talked about that it's a lot easier to take the root to make something smaller before you make it larger. So here, if you took the cubed root of 27, now that is an odd root of a positive number, so there's one solution, which is 3, and then square it, you would get 9. And up here you see that we are squaring the 27, making that 729, and then you've got to try to figure out what the cubed root is, and that's a harder road to travel versus the making something smaller before you make it larger. So today, we're going to take what we learned with the nth roots, and we're going to combine that with some of our exponent rules as well. Before we move forward, here's just another example, hopefully encouraging you to take that root, in this case, the square root of 16. This time it is an even root of a positive number, so we're getting two roots, two solutions, plus or minus 4. And when we raise that positive 4 to the third power, we're getting positive 64. And when we raise that negative 4 to the third power, we're getting negative 64. If you look at the other road you could have traveled by taking that third power and then the square root, it is a much more difficult road to follow. Okay, so let's look at some other problems that are going to combine these ideas with our exponent rules. So if you look here, we have a common base that's being multiplied, and when you multiply common bases, you write that base and add the exponents. So that's kind of where we're heading here. To add fractions, of course, we have to have a common denominator. The 1/2 would be 2/4, and we would get 5 to the 3/4. And that's as simple as that one is going to become for us at this point in time. As I look at problem B, I'm noticing quite a complicated mess here until I see that both the 2 to the 4th and the 3 to the 4th share this exponent. So I could rewrite that problem and put that 2 times 3 to the 4th power. Now that becomes 6. And 6 to the 4th power raised to the negative 1/4. When we raise a power to a power, I'm going to multiply 4 times negative 1/4, which would give me 6 to the negative 1. I was just showing you that step. And to convert that negative exponent to a positive exponent, I'm going to reciprocate and end up with 1/6. And in this case, making that power of 1 the invisible 1, 1/6. And see, I'm noticing this time a common base with a quotient. And remember, our division rule said if you have a common base, you write the common base and subtract the exponents, top exponent minus the bottom. So we would have a common base of 7 to the 1 minus 1/3, which would be 7 to the 2/3. Let's take a look at some other problems here. So as I go to the next one, I again notice that these two bases of these two powers share the same exponent. So I'm going to put that 12 to the 4th to the 1/3. So I'm going to have to square it in a minute. And I notice right away that 12 divided by 4 is 3. Again, just trying to simplify this as best I can. And when I raise a power to a power, I'm going to multiply these exponents, and I end up with 3 to the 2/3. The next one that I am seeing here is I'm noticing a common root. So what if we were to paste that root back together? so that the 4 times 16 becomes the radicand, the number underneath, and we have a single cubed root. We can cut a root across multiplication or division, not addition or subtraction. And now I see that 4 times 16 has bought me something, because the cubed root of 64, 64 is a perfect cube, and an odd root of an even is going to give me the single answer of 4. Now you need to understand that sometimes we can approach this from a different angle. So I could have taken e and made both those rational exponents to start, again putting the index as the denominator and the invisible 1 exponent as the numerator. Again, I could kind of paste this together and make it 4 times 16 to the 1/3. Changing the 16 to 4 squared so I would have a common base. Now I have 4 to the 1/3, and when you raise a power to a power, you multiply. And when you multiply, you add the exponents, and I'm still going to get to that 4, but just a different root. And speaking of roots, I think that the root way is probably an easier way to go there. On the next one, again, the idea that we've cut this root apart, I can't see anything. There's no 4th root of 2 that is a whole number. Same thing on the top. So what if I paste this root together and have the 4th root of 162 divided by 2? Am I heading in a direction that will kind of clean this up? 162 divided by 2, is 81. And I recognize 81, that the 4th root of 81 is a whole number. It's an even of a positive, so there will be 2 answers, and it will be plus or minus 3. Last example on this page, I'm taking a look and kind of seeing what could I do with this. I don't have a common root, so I kind of can't glue these back together. So I'm thinking, what about if I change them to my exponents and then use my exponent rules of raising a power to a power? I would get 1/3 times 6, which would be a squared exponent, and 1/2 times 6 would give me a cubed. And then 3 squared is 9. 3 cubed is 27. Or if we look here, we've got a common base. Why not just write that as 3 to the 5th? And if we needed to simplify it, we could raise 3 to the 5th power. So what I'm going to do now is just show you 4 examples here. And I would encourage you to just pause the video and see if you can do these yourself. And in a second, we'll come back and I'll unveil the answers and see how you did. Okay, so hopefully you've tried these 4. Common base, multiply. We're going to write the base and add the exponents. And 1/4 plus 3/4 is 4/4, which is 1. So I've got 5. Next one. Common exponent here. So what if we put 80 divided by 16 all to the 1/2 power? Would that get us any closer to cleaning this up and simplifying it? Well, 80 divided by 15 is 5, and I'm going to leave it there because the square root of 5 is an irrational number, and it's probably just best to leave it as 5 to the 1/2. Wow, look at 64 is a perfect cube. So the cube root of 64, we're going to get a single answer here because it's an odd root of a positive. So that would give me 4. And then the 4th root of 81 is an even root of a positive, which is going to give me 2 roots, 2 solutions. In that case, would be plus or minus 3. Now, if I take 4 times the positive 3, I get 12, and 4 times the negative 3 is negative 12. So my final answer there, plus or minus 12. Boy, that was a really nice simplification there. And finally, on this last one, I'm going to take that 4 to the 3rd. I can't see taking the square root. Nothing's kind of going to simplify. We don't have the same base. We don't have the same exponent. So I'm going to raise these to the exponents. And when I do that, I notice that I can divide 64 by 4. And that gives me a perfect square of 16. Since I'm taking an even root of a positive, there'll be 2 answers. And it's plus or minus 4. So I hope that you enjoyed this lesson on simplifying radical expressions using our exponent rules. Next up, we're going to put some variables in there. Have a great day, everybody.